Hello, my name is Freark Westra, and together with Peirs, Sabine Molenaar and Slinger Jansen, we have written the paper The Influence of Technical Variety in Software Ecosystems. For many companies, selecting the right programming language is an important decision to make in what language to develop or learn to develop in. Different kinds of programming languages offer different kinds of benefit. To decide on a programming language, a language can be considered as a software ecosystem with many actors providing code chunks that offer other actors benefit from. A concept that aids the decision is the health of a software ecosystem, which is defined as the longevity or propensity for growth. More commonly, an ecosystem is considered healthy when all actors are satisfied. Tugana et al. Theorized that, similar to biological ecosystems, software ecosystems are considered to be more healthy when there is more diversity. In programming languages, this diversity can be expressed as the degree to which it provides a variety of technical solutions. Higher technical variety opens up new opportunities and thus better niche creations. Ultimately, this delivers improved software ecosystem health. Compared to general-purpose languages, domain-specific languages can offer better learnability for domain experts, but they also imply limited capabilities and a loss of processing speed. To measure the technical variety, current research only mentions conceptual metrics for technical variety and methods that are difficult to operationalize. In 2014, Jansen introduced OSEO, which organizes a set of operationalizations in 3 silos: productivity, robustness, and niche creation. We theorize a new operationalization for measuring software ecosystem health by associating the technical variety with OSEO metrics and comparing its value for different programming languages. The goal of the research is to uncover a relation between technical variety and ecosystem health. We divided this in 2 research questions. The first one being, what are the influences of technical variety on software ecosystem health? We compare technical variety with robustness and productivity, whereas the independent variable is technical variety and the dependent variables are robustness and productivity. The second research question is, what are the differences between the technical variety of general-purpose programming languages and domain-specific programming languages? We compare the technical variety of general-purpose programming languages versus domain-specific programming languages, whereas these are independent variables and technical variety is the dependent variable. We came up with 3 hypotheses. Research question 1 has the first 2. The first one states technical variety within a software ecosystem has a positive effect on the robustness of a software ecosystem. The second one states technical variety within a software ecosystem has a positive effect on the productivity of a software ecosystem. The hypothesis for research question 3 states general-purpose programming languages have a significantly higher technical variety within the software ecosystems, opposed to domain-specific programming languages. For operationalization of technical variety, we scraped the descriptions of GitHub repositories and searched for matching terms with a glossary of topics comprised from the 20 most popular programming languages according to the TIOP index. To gather robustness, the active contributors of these repositories were scraped. An active contributor is a contributor with at least 1 commit in 2019. To gather productivity, the number of commits in 2019 of these repositories were scraped. Both are metrics mentioned in OSEO. And as you can see for hypothesis 3, the metrics are collected for 4 programming languages, 2 general-purpose programming languages and 2 specific-purpose programming languages. A domain-specific language is a small, usually declarative language that offers expressive power focused on a particular problem domain. In our case, this is R and MATLAB. And if it doesn't match that definition, it's a general purpose programming language. In our case, Python and Java. To enlarge difference in variety, the most popular general purpose languages are compared with the least popular domain-specific languages. To gather the data, different transformations are executed. These can be read in our paper. For the research, a JavaScript web application is written for this research. This is made publicly available on GitHub. The length for the programming languages average at 9.25 words per description, with a standard deviation of 6.67. The length has a right skew of 2.71 and a kurtosis of 12.42. We say this because the length of the descriptions might harm the validity of our research. Luckily, the length per programming language were comparable. Our results show that many occurrences explain a lot of productivity in that language for that word. For instance, you can see Java is very informed with the word Android. This is logical since Android is developed in Java. And Python's most popular term is TensorFlow, a familiar framework for machine learning. Java and R have one or two topics that are more popular than the remaining topics, as can be seen in the graphs on the right side of the screen. This table shows that technical variety is higher for general purpose programming languages. Additionally, we calculated a ratio that shows how many words per unique topic are required. It is remarkable to see that domain-specific languages require more words to introduce a new topic. This might indicate that domain-specific languages have more elaborate descriptions. On the contrary though, general-purpose programming languages show more unique topics per repository. So, looking at hypothesis 3, that addresses the influence of technical variety of general-purpose programming languages versus domain-specific programming languages, we did two statistical tests. First, we did a Welch 2-sample t-test on the number of topics per repository. And then we did a Welch 2-sample t-test on the number of unique topics in the first quartile range of topic mentions. Both are statistically significant, but both are rejected. That's because there's a big difference in technical variety between specific purpose programming languages R and MATLAB, as can be seen in the green circle. For hypothesis 1 that concerns robustness, a Peirs product correlation coefficient between technical variety and number of active contributors in 2019 for the top 1,000 topics of all languages is done. This proved to be statistically insignificant. Hypothesis 2 that concerns productivity, a similar test was done, but this test was a product correlation coefficient between technical variety and the number of commits in 2019 for the top 1,000 topics of all languages. This was statistically significant, albeit it would with a very minor relation. So it's debatable whether the effect is actually evident. When looking at the correlation graph, it can be seen that the uncertainty increases when the number of topics increases, which seems logical as contributors often specialized in fewer topics. In this research, 3 different statistical approaches are used to explain technical variety. The first one being the number of unique topics per language, the second one being the share of topics that are mentioned just once, and the third one being the share of the number of unique topics in the first quartile range of topic mentions. These approaches all express a different form of variety. Hence, we choose to specify what these forms describe. On one hand, you have regular variety, which describes the convenience a software ecosystem offers to seek for business opportunity in a well-established niche. On the other hand, we have specificity, which describes the degree to which a software ecosystem offers opportunity in unique, unexplored niches. For the number of unique topics per language, the definition of variety can both be regular variety and specificity. Share of topics that are mentioned just once describes specificity, though, as there's a there with a high number of topics, a high share of topics that are mentioned just once, there's a high degree of specificity. The third one, the number of unique topics in the first quartile range of topic mentions, describe the regular variety, as these are the most popular terms in a programming language. We have two examples per definition. For regular variety, popular terms are for Java are Android, and for MATLAB, for instance, algorithm. These terms are used a lot, and the chance of establishing a niche related to these terms are rather high compared to the terms FFmpg for Python and R for Tesseract. Both are very specific topics that are only mentioned just once, and the chance of creating a niche for that specific topics is rather small. The main discussion of this research is, firstly, this research has not taken all opportunities that GitHub provides for gathering robustness and productivity metrics. So the chosen metrics might be poor proxies for what they describe. Possible metrics to describe are the contributor ratings for robustness, reputation for robustness, and the bug fix time for productivity, and the usage for productivity. Secondly, selecting general purpose versus domain-specific languages always implies a different variety. So no explanatory comparison is possible on the software ecosystem health of the programming languages. And thirdly, languages can be general purpose and domain-specific at the same time, according to our definition. For instance, Python can be a specific purpose, domain specific for machine learning, but it is domain general purpose for all other stuff it can do. The main conclusions of this research are, firstly, that no relation between technical variety and productivity or robustness can be proven. Secondly, general purpose programming languages do show a higher technical variety than domain-specific programming languages, but this can be interpreted in multiple ways. Possibly, there are two new interpretations for technical variety as an indicator for niche creation. First one being regular variety, which explains the convenience a software ecosystem offers to seek business opportunities in established niches. And secondly, specificity, which explains the degree to which a software ecosystem offers opportunities in unique, unexplored niches. The future use of these terms in software ecosystem health research is dependent on their effect on niche creation. And this is something future work might empirically gather. Secondly, this research would be strengthened by improving linguistic interpretations. This can be done by using topic mining, which focuses on finding word groups, or creating correlation clusters to uncover patterns in often paired words. A third step that is very promising is the gathering of GitHub repository topic labels. These are labels specified by repository authors. The table to the right shows a table we set up as an example for how promising the method is. The table shows more interesting topics for all programming languages. This method does have a strong bias though, since a vast difference in the number of topic labels for each repository is present. Thank you for your time, and we hope our paper sparks interest, an interesting discussion, or inspires future research. Our team will be available for a Q&A after our presentations. The references for this presentation are shown on the next slide. Thank you very much.